Hello and welcome to Math with Me. We're going to be talking about tree diagrams today in 7.4. You can see a few representations of tree diagrams on the screen at this point. A tree diagram is simply another way to represent all the possible outcomes of an event. The end of each branch represents a combined event, right? So you have some examples here of tossing a coin. You've got some pizza options, crust, cheese option, and then topping options, and then a little bit more specific notation wise. These are all examples of tree diagrams, and we're going to work on creating these right now, and then a little introduction to using them. So our main goal is these three things: talking a little bit about compound events, a little bit about with replacement, without replacement, and then using tree diagrams to find probabilities. Okay. So compound events, or sometimes referred to as combined events, is the probability resulting from two or more events considered together. So if we take a look at two events, they are independent if one event does not affect the occurrence of the other. This would be like if you flip two coins. You flip one coin, you get a head. That will not determine what happens with the second coin. Okay? So those two things would be independent. Independent events, the probability can be calculated by taking the probability of each event happening and multiplying them together. We can expand that to more than two events. So if you have three events or four events, if they're independent, then you can just multiply the probabilities of each event happening and multiply them together to get the combined event. Okay. We're going to work a little bit on setting up some tree diagrams to begin with. The first few are fairly straightforward. If I want to represent tossing a 5-cent and 10-cent coin, then I'm going to start with the first coin, 5 cent. And for a 5-cent coin, there are two options: heads, tails. And then after I record or notice whatever happened, the second coin, when I flip it, if I got a heads for the first one and a heads for the second one, that's a unique event or a unique outcome. If I got a heads and then a tails, that's a unique outcome. If I got a tails on the first one and then heads and then tails and tails, those are all unique outcomes. And that's what this tree diagram shows me. The ends, if I travel down the branches to the ends, that will let me know how many total unique outcomes there are. For the next one, I'm tossing a coin and twirling an equilateral triangular spinner labeled A, B, and C. So again, the first thing is a coin. So the first set of branches represent the outcomes for the coin. So I get heads or tails. So regardless of what outcome happened the first one, there are still three outcomes for the spinner. So if I got a heads, then there's the opportunity to get an A, B, or C on the spinner. If I got a tails, same thing. The most common mistake that I see you guys doing when you set these up to begin with on your own is trying to represent all of the possible outcomes in that first pair of branches. So I see a lot of this. So heads, tails. So that's a common mistake when I see you guys trying to set these up on your own. Each pair of branches, you can kind of think of it as splitting them off into whatever the specific things that are happening into each of its own sets of branches. Okay, so this, no good. All right, for letter C, twirling two equilateral triangular spinners. So the first spinner has 1, 2, or 3, and then regardless of if you got a 1, 2, or 3, the second spinner also has 3 options. Okay, so in this case, there are a total of 9. There are 9 different possible outcomes in this combined event, right? And you can count those by traveling down each of the branches to the end. You can see there are 9 ends of the branches. For letter D, drawing 2 tickets from a hat containing pink, blue, and white. So 3 colors, again, kind of like the spinner one, 3 options for the first ticket, and then the second ticket, also 3 options. Now, these 3 A, B, and C are it's kind of safe to assume that these things are all equally likely. But for letter D, we're not so sure. It just has a number of pink, blue, and white tickets. And if that's the case, then maybe there's only one pink ticket. So think about how that might change your tree diagram if there's only one pink ticket. Well, if you pull out the pink ticket for the first one, there's no more pink left, so that's not even an option. So that's where identifying the probabilities really helps us clarify the situation. We're going to do a little bit of that right now. And we're going to take a look at one event here and the experiment. The experiment is we've got a jar of dice, and there's 4 dice that are yellow and 2 that are white. And we're going to take a look at 2 situations. One situation where we draw 2 dice, and we do that so that when we draw the first one, we put it back, and we call that with replacement. In the second situation, we're going to draw the first die and then set it aside and then draw a second one. And we're going to see what that does to our outcomes. So if I'm going to draw a tree diagram to represent this situation, I'm thinking of it as 2 draws, right? I'm drawing out two die, and let's see what happens here. So in my tree diagram, for that first set of branches, right, my first set of branches, I have a yellow and a white. So that first set of branches represents the first draw, right? So these are the outcomes for that first draw. For the second draw, again, it's not that there are multiple yellows outcomes and multiple whites. These are the possible outcomes if I get a yellow for the first one, and these are the possible outcomes if I get a white for the first one. So again, this tree diagram shows me that there are 4 paths to the end of the tree. So 4 paths, and so there's 4 different outcomes that could happen. And so what we want to start thinking about are, okay, the probabilities, because we know these things are not equally likely. There's 4 yellow and 2 white. So that's where we're going to start labeling some probabilities here. And so for that first draw, there's 4 yellows and 2 whites out of 6 total. So think about we draw one out and then we put it back in. So for that second draw, there's still 4 yellows and 2 whites. And same for the other situation, 4 yellows and 2 whites. Okay, so nothing really changed here in the second draw. So then what I want to look at is the probability of each of these combined events. And so that's where you're going to start seeing some labeling on the ends of each branch. So if I wanted to figure out the probability of getting a yellow and a yellow, I just need to multiply down the branches of the tree. So this notation is telling me that this is the probability of getting a yellow and a yellow. And that's simply gotten by taking 4 out of 6 times 4 out of 6, gets me 16 out of 36. For the yellow and then the white, 4 over 6 times 2 over 6 is 8 over 36. Same thing for this branch and this branch. So these are the probabilities of each of these combined events. So white and white is 4 out of 36. That's the least likely. It looks like yellow and yellow is the most likely. Think about why that makes sense. There's 4 yellow dice. So that's the greatest possibility to get yellow versus white. Okay. So the outcome we're really looking for here is that top branch, right? 4 out of 6 times 4 out of 6 gets me 16 out of 36, or 0.444. Let's take a look at what happens if we are going to not replace, right? So without replacement. We're going to start with the same tree diagram, but since we are not replacing, think about what happens to the second draw. So the first draw is still the same situation, 4 out of 6 and 2 out of 6. The second draw, though, really depends on what happens on the first one. So first of all, if we are taking a die out and not putting it back in, the total number of die, right, or dice, is now just 5. But then think about, okay, so what if we take out a yellow one? The probability that we get another yellow one decreases, right? So notice that decreased by 1. There are still 2 white though in this situation. But if we go down the white path first, then there's still all 4 yellow left, but now the white has decreased by 1. Okay. Again, if you notice, each of these pairs of branches add up to 1, right? So each of these pairs combined together should add up to 1, because you have to get a yellow or a white in this situation. And then for the second draw, you either get a yellow or a white. So these pairs of branches, they add up to 1. Those are complementary events. Okay. So the event we're actually interested in is the yellow and yellow. I went ahead and just wrote out the probabilities of each of these combined events, but we're really just interested in that yellow event, which is 12 out of 30 or 0.4. So notice if you compare these two without replacement, the probability of getting yellow and yellow decreases a little bit. Let's take a look at a couple more questions related to the first diagram. So with replacement. So we take one out, we look at it, we put it back in, and then we take out another one. So the probability of getting at least 1 yellow. So a tree diagram can not only show us the probabilities of the combined events, but then we can use those to figure out the probability of other things. So getting at least 1 yellow, what I want to do is identify all of the branches that fit that criteria. So getting at least 1 yellow. This branch fits that criteria. That's yellow and yellow. This branch fits that criteria. That's yellow and white, at least 1 yellow. This branch fits that criteria where I got a white and a yellow. It's the last branch that does not. So getting at least 1 yellow, all 3 of these branches fit that criteria. So what I need to do is add all of those together. So I'm going to add each of those together. Since I already have a common denominator, that's pretty easy. 32 out of 36. Okay. For part B, getting 1 of each color. So I want to find the probability of getting 1 of each color. So again, what I need to look for are the branches that represent the outcomes that are just 1 of each. So a yellow and a white, or a white and a yellow. And those are the 2 middle branches. So those are the 2 branches that I need to add together. So 16 out of 36 is the probability that I would get 1 of each. And then for the last one, getting no yellow, that's just back to the simple calculation of multiplying down the branch, which we already did. And so that's just 4 out of 36. One thing I just want to point out here is that the probabilities from A and C. So the probability of A was these 3 probabilities. The probability of C was this one. That includes our whole sample space. So those 2 probabilities added together equals 1. Right? And that should be the case. Those are what we call complementary events. You either get at least 1 yellow or you get no yellows. One of those 2 things must occur. Okay. Just to clarify, again, when we use a tree diagram, the probability for each branch is calculated by multiplying the probabilities along that path. So when you're traveling down the branches, you're multiplying along, and that's the probability of that combined event at the end of that branch. If multiple branches then fit a certain criteria, then we take each of those ending probabilities and we add them together. Okay. So to get the ends, you multiply down the branches, but then if multiple branches fit a certain event, we need to add those probabilities together. Last thing I want to do is get you started on this problem, and then you can do as much as possible on it and bring your work to class. Pause the video, familiarize yourself with the situation, and then I'll help you start the tree diagram. Okay, so the one thing I want to point out here is, or kind of get you started on, is the beginning of the tree. You can kind of see that we have information related to whether snow accumulates or not. And so what I'm going to suggest is that you start with the accumulation. So in your tree diagram, snow either accumulates or it does not, and that's what this little apostrophe thing looks like, or reads, is this is accumulates, this is does not accumulate. Right? That's the notation specifically to say not this thing. So accumulation, non-accumulation. So then based on whether it accumulates, you can show what happens and the probabilities, and when it does not accumulate, what happens and the probabilities associated. Okay, so try to set up that tree diagram and then use your tree diagram as much as possible to answer these questions.